I'm actually going to talk about something a little bit different. You imagine this could be a vendor talk. I could just talk about the products that are available. I'm going to take a bit of a different twist and talk about what I think, where I think this is going and where I think Intel is going to be able to get there. And I'm going to do it from the lens of something that has always made me angry, which is the distinction between the network inside your computer versus the network outside your computer. And I feel like this is all just a continuous whole. So I'm going to tell you a little bit about who I am, a little bit about networking at Intel, and then back into a historical perspective of how historically the network inside your server versus outside your server were actually quite different. And then how I think this trend towards bigger and bigger supercomputers is basically flattening that out. And then I'm going to talk about how I think, at least if you look at existing technologies, there's a pretty clear trade-off between scale and deterministic performance, where deterministic performance is, of course, key for this group. I think most of you have heard of a term called a power wall, which I'll cover if you haven't, and introduce a new term that I'm calling the power density wall. Use that to derive sources of non-determinism, and then go to kind of my claims that are somewhat intentionally controversial, which is that the two networks, the one inside your server and the one outside your server, are actually going to converge over time. And that a key technology of optical I/O is going to help get them there. And hopefully by the end of the talk, you agree with me. If not, we'll have a much better conversational time. A lot of people don't know, but Intel does a lot of networking. Actually, this is the context for both me and for Intel. I should actually even start further back. 25 years ago, I got my start doing network and storage and system admin at University of Maryland in their HPC lab. So really 25 years ago, I was writing MPI, debugging systems and whatnot. I've gone on from there to do primary research, which got me stumbled into the group at Stanford that started SDN, which got me into shipping production net products, and then back into research, and then back into running large networks at Facebook. Now I'm back into products. And so I've kind of bounced up and down the whole stack of networking. And part of the reason why I'm at Intel is that Intel actually owns the whole stack of networking. They do optics in terms of silicon photonics. They build switch CPUs, they build switch ASICs, they build smart NICs, foundational NICs, and infrastructure processing units, and a whole slew of software, including libfabric and the IPDK project that I'm working on, and other things that end up being relevant for this group. And so I'm at Intel because they own the whole stack, and it is possible to do kind of end-to-end optimizations in that type of space, and that's the thing that most excites me. By the way, this is a small enough group that we can make this interactive, and my talk style is intentionally a bit controversial, trying to incite folks to ask questions so we get more interactive, because I feel like that makes for a better thing. So if I say something that finally pushes you over the edge that you want to ask a question about, do it. That's somewhat by design. Historically, if we look at the network outside of our servers, they're complex. They're many-to-many. You have unicast host-to-host, but you also have multicast, you have broadcast. They're inherently asynchronous, they're inherently distributed, and there's this long tail of alphabet soup of protocols in terms of BGP and MPLS and all sorts of things here. Unfortunately, I've coded most of these things.
Sorry, I forgot to do one small thing. I apologize.
Oh, okay. Fortunately, nothing's been groundbreaking so far.
No.
Sorry.
Does anyone feel like their life has been changed and I should start the talk again?
No. Amit, are you able to see the slides?
I can see, yes, thank you.
Okay. Sounds good.
And if you wanted decent performance, you basically had to over provision the network or try to add quality of service, and adding quality of service can be a pain. And long story short, you have congestion and unpredictable performance. That's the world that's kind of outside of your servers. And if you look inside your servers, historically, it was very different. You have these kind of high-speed buses, you have these point-to-point systems. Imagine a world where before NUMA, you have a single socket, you have a single memory controller. Life is simple, it's synchronous, it's decentralized, relatively simple data plane protocols, PCIe, uniform memory access. Really, you don't need quality of service because you have synchronicity. You have very low contention. As a result, you have predictable performance. But that's not the world that exists right now. You know, as you fast forward to the modern day, even inside your server, you have a much more unpredictable network. You have NUMA, you have multi-socket devices, you know, with UPI or similar things. You have virtual machines with a virtual switch, so you actually have different contending bodies. You know, SRIV, you have offloads to GPUs. There's a whole bunch of offload protocols. You might not even have local storage. You might have disaggregated storage. There's a whole lot more going on inside the box. And you have things that add contention. You have CXL, you know, the various flavors of that. You now start to need quality of service inside the box. I'm curious, just with a show of hands, how many people have been personally bitten by the noisy neighbor problem? No one? All right, I spent 5 years at Facebook fighting this tooth and nail. Like it's a real issue. And the long, hard result is that just because the packet was delivered to the NIC doesn't mean that you're actually going to receive it in your application. That there's actually performance problems in the network local to your server that cause issues. So that's one side of it. But the other side is people are now requiring more and more predictable performance for the network outside their device. And I feel like that's basically what this workshop is you know, how do I get predictable performance outside the network? And just to put a name on what everybody's already thinking, you know, HPC is deeply pipelined, it's deeply parallel. A single packet loss can cause a pipeline stall, which you know can have an outsized impact on job performance. You know, in a deeply parallelized, synchronized environment, you know, for example, you know, I'll reduce, I'll gather, or something like that. It really breaks the statistical multiplexing assumptions that best effort Ethernet is built on. And it would almost start to look like a denial of service at some level. And it's hard to make a network at large scale perform predictably like this. And then, of course, there are these things called supercomputers. And I call them supercomputers with quotes because when I first started, they were actually physical, you know, single device computers. So I was working with CM5s, CM2s. And those were the network inside the box. But of course, we know that that network, you know, just because it's inside a sheet metal doesn't really matter. You know, and if we start to look at modern systems like Aurora or Frontier, it's those very similar designs outside the box. And this distinction of inside versus outside the box, I think is pretty arbitrary. And then, but if you look at the way that you design HPC networks versus large data center networks, they're actually quite different, right? So a large data center network, you probably have best effort Ethernet, you have ECMP, you have a Clo fabric, and you have TCP on top of that. You know, in modern HPC, you would have something that looks like Aurora or Frontier, you know, Ethernet, low latency, adaptive routing, you know, probably a Dragonfly topology instead of Clo. And the idea is you're trying to have a low average, but critically a low P99, kind of a long tail. You're trying to reduce that latency as well. And so that's certainly the HPC view of the world, that you know, these long tail performances kill us. A thing that I'm not sure has made it to this community is that the Facebooks and Googles and Microsofts of the world care about this too. Huge fractions of their workload are RPC based, which look a lot like HPC workloads in terms of small message size, and long tail latencies kill you. And so these historically divergent types of networks are converging, is my claim, because the workloads are converging. And if you start to say, all right, well, let's look at AI training, everybody's looking at AI training. So that's going to be another forcing function here. So I threw together this slide to try to make the point. Folks can argue, it drives me nuts how different versions of PowerPoint will render things differently. Imagine that the triangle and square are actually lined up correctly. So what we have here is a graph of, and it's all log scale, so don't let that trick you. Scale in terms of the number of nodes for the y-axis, and latency in nanoseconds to access a single 1 byte uncached entry. So, and then the triangle is the P50 access time, and the circle is the P99. And these are order of magnitude. So if you disagree slightly on the displacement, we'll let that slide. If you disagree kind of in a broad stroke, let's talk about that. So in a historical unified memory architecture, there really wasn't a lot of performance difference between your typical case and your P99 case. But you could access 1 byte pretty uniformly. But if you jumped up to, say, an 8-socket device in a NUMA architecture, it actually starts to take more time to access some of the memory than it does to access others. And so that starts to add to non-determinism. So then you get into interesting memory layouts, you get to application performance, and these things start to affect application design time. But what about a typical HPC cluster? Not even something as big as Frontier. So we're looking at, if you can get 1 byte access times on the order of single-digit microseconds, that's pretty good, right? In the common case, and you could imagine some level of congestion where you get into maybe tens of microseconds or hundreds of microseconds, like in the kind of longer tail case. That's a pretty good system, I'd say. But you're looking at an order of 10,000 nodes there. But if you look at a Google or a Facebook size data center, they jump up another order of magnitude or 2 in terms of the size of the number of nodes, but they start using congestion control protocols like TCP, which in the typical case have roughly the same order of magnitude for access time, but the backoffs that you get out of TCP, the timeouts and whatnot, those can take you out an extra order of magnitude or 2 in terms of the P99. And that's local to the data center, and a lot of computations that they do are actually data center to data center. And once you start going data center to data center, you pick up speed of light delays, as well as an additional set of, well, maybe you don't just have a single packet that gets lost. Maybe you get, in the P99 case, maybe you could have a pathological case of a couple packets out of the same flow get lost. And so if you believe these rough numbers, there's actually a pretty clear trend line here that shows that just from empirical data, there's a trade-off between scale and the non-determinism of the system. And as people who are trying to design large deterministic performance systems, this should scare you, right? This is bad. And so the question is, how do we fix this? I haven't said anything controversial enough for someone to ask a question yet. Come on. Yes, sir.
So this assume that those are randomly used, and in HPC the workloads are parallel, so the jobs are allocated to the same leaf switches or same group of the open network. So in that case, maybe the P99 frequency maybe
Better.
More.
Let me repeat your question for folks online and to make sure I caught it right. So does this data kind of assume kind of a random access pattern such that if you had a more intelligent layout and locality, I'm assuming in an HPC system, that you might actually have better performance here, and that this graph might be shifted left? Is that kind of your question? Yeah, so I mean, admittedly, these are order of magnitude numbers, so you take them with a grain of salt. But when I put them together, it was based off of, not all of your accesses can be local. It can be, close. And so if you imagine a distribution of, maybe your top 20% are close, but then the 50% of accesses is really what I'm trying to show here with the triangle. And then the square of the P99, that is kind of the worst case of them. Not the worst case, because you could start to go to P99.9.9, but it's the intuition I'm trying to appeal to is, as you get to bigger systems, you have bigger problems, and at a certain scale, you have a constant number of problems. There's always, once you have a 10,000 node network, there's always going to be one node that's down. And I guess maybe I should have called this a P99.9. to draw out that case. But at an intuitional level, does that make sense? But thank you for asking a question. Sir. Say again?
And I find it kind of utopic that if a node is down, we can restart a node in 1 second.
You're saying if a node goes down, you can restart it in 1 second?
I find the idea that we can restart it in just a second.
Oh, to be its own topic.
New topic.
Oh,
Impossible.
oh, okay. Yeah. So yes, and so and take whatever failure rate you want, map that onto a graph like this. There is, when you start looking at the long tail of performance, and maybe I'm biasing by my background, where the number of nodes is on the really off the scale here. In the background that I have, if you have a failure rate of even as low as 1 in 100,000, once you're dealing with millions of nodes, that means that you're having multiple nodes fail on you daily. And if you have a large job, that's really where the HPC community, and even more particularly the AI training community, is heading. It speaks to the need of checkpointing, but it also speaks to, okay, how do you start to avoid this long tail problem? And what's a little bit hidden here by the log scale is, as you go more this way and more that way, you're dealing with an increasingly worse problem. So why don't we just give up on scale out and do just focus on scale out? Let's just, if it's hard to do things further and further out, why don't we just do more things locally? And I'm curious, just by a show of hands, how many people have heard of the power wall? This is a slide I've stolen from my colleagues at Microsoft with permission. Not many people raise their hands, so I'll go through this quickly. The insight is, if you look at a data center or a large HPC node, and you look cluster, and you look at the fraction of power that's used for compute and the fraction of power that's used for networking. The fraction of power that's used for networking appears to be going up as the speed to the server goes up. And from an operator's perspective, the fraction of power that goes to the network is actually pure overhead. You're getting less compute out of your power as a result of that. And this trend is really disturbing. So it's basically saying, at 10 gigabits per second to the server, there's not much power loss for the network. You can optimize power for the network, but it's not that big a deal. But as you get to 400, 800, and once you start getting multiple 400 or 800 gig links to GPUs, it starts to dominate it starts to dominate the overall cost of the power. And that's bad, right? And so as I said, this is not my data. This is data from Microsoft. I'm using this slide with permission. And maybe you can argue that if you actually normalize this by link speed, you are getting performance efficiencies by link speed. So the picojoules per bit is going down over time, but not proportionate to the speed. So, and it's causing the trend to go up. So this is something I thought this community would know. It's a slide that I've certainly seen a bunch of times. I'm going to introduce, so this is an issue for building bigger and faster networks. So if you want to get to, zeta scale, and you're assuming you're going to do it on, an 800 or higher link speed, this is a problem. I was trying to introduce a new topic, which is what I'm calling the power density wall, which is, the laws of physics are always going to be a limit. I don't know how to dodge those. And as a result, there's a limit to the amount of cooling that we can do. And so as a result of that, there's a limit that we can actually do in terms of scale up, which I mean is kind of computational elements in a local box, in a local rack. We're always going to be forced to do more and more scale out just because of cooling. Admittedly a hand-wavy argument, but I think one that's true. Electrical systems will always dissipate heat, and they will always dissipate more heat as the clock speeds go up and as the number of gates go up. And that seems hard to argue with. Certainly there's efficiencies over time. we've already had to move to liquid cooling to address this. There's not that many additional cooling technologies beyond this. This seems fairly fundamental to me. And as a result, I make the claim that if you look at the rate of scale up, that is, how many compute elements per device versus scale out, which is how many devices you have, the ratio of those things will actually trend to 0 over time, which is, the number of devices, compute elements inside a server is going to stay roughly constant. It seems really hard to get that to scale, with the number of nodes that you need. And as a result, most of your scale is going to come from the scale out. This is an intentionally contentious topic, and no one's willing to fight with me on this. This is what I get for giving the early morning talk. I should have kept the afternoon session. No one disagrees?
Well, except for the PTX2 or like selling super parts, this seems to be the frontier seems to be kind of going on. I don't know. Why would you think this is contentious that you would definitely need scale out and scale up will give the bottleneck?
I think the scale up will remain bounded, and that as we want additional, if we want to get to zeta scale, I'd love to attend the next Zetacom, if you want to call it that. I don't think we get it through scale up.
So have you thought of these Cerebrus kind of systems, like basically supercomputing in a box, like custom built systems?
I mean, it really fundamentally comes down to how do you cool them, and like take that system, which admittedly I'm not familiar with, and how do you get it to 10x the amount of density? I think you don't, right? And zeta scale implies 1000x.
I might take issue on the previous slide.
Laptops is not that wet.
When to normalize 100%, it's kind of you can't handle that kind of stuff very easily. The more you combine the words, the non-parallel part for the hard to use by communications, and what kind of gets lost there is that the amount of compute we still grows, and even here at 99.999% of overhead for networking, and we can still do enormous amount of compute. Serverly, I'm not sure it is. I understand, but I don't like existential threat, just a technical challenge where we might have to grow slower and.
The question is, so actually, let me repeat the question both for the folks online to make sure I got it. So you're saying is what's being hidden under the covers here is the blue chunk is being normalized. The actual compute potential of the blue chunk is being normalized away because it's increasing a huge amount.
Yeah.
And
the 10 and 40, there's 148. The 10 bar should be 10%, 25%, 45%. That's a 4x in between.
I agree with that, but, and I didn't kind of get to my main point on this slide, which is I think practically there is a power density limit, which is, at least in practice from what I'm seeing, is something in the order of 30 to 60 megawatts per site. And so while the amount of compute is going up, I think the total power that you can have in a physical location is roughly fixed, again, based off of power grid densities and whatnot. And maybe you could argue you could get up to 120 megawatts or something like that. I don't think anyone's going to argue that you could do 10x this, right? And so if you believe that the total amount of power in a physical location is bounded, again, based off of laws of physics and existing power power distribution realities, I agree that the compute potential of a given site will go up with technologies, but I think losing more and more of the total power, which is ultimately what I think is going to be the limiting factor, ends up being the power wall issue. And from my past lives, an interesting thing is if you approach a power company and say, no, I want a lot more. No, a lot more. Maybe the national labs have magic that commercial companies don't, but there's no check that you can write to a large power company that lets them kind of build an extra reactor based off of a cloud service provider's model, because they might be gone in 50 years. And the electric company might still be holding the foot for the cooling, the extra hydro dam or whatever they built to supply that power. Yeah, sorry. I only have a couple more slides. And I thought it was going to be short. So where does this, where does the non-terrorism come from? So again, kind of a log scale chart. A little bit of the non-terrorism comes from NUMA. If you look at, say a three-tier closed topology network, the number of hops you hit going from node to node might be 1 or it might be 7. And so, there's variability based off of the number of hops, and that's if you assume there's no buffering on the switch. If you assume that the switches actually hit their full buffering, which is the other side of that peak, the amount of time you take to go through a full buffered switch, even if your packet doesn't get lost, is actually substantially bigger than the port-to-port latency on that switch. So if you just run quick numbers, a typical 400 gig switch, 32 port 400 gig switch, typically has average 2 megabytes of buffer per port. And if you say, okay, well, how long does it take to drain 2 megabytes of buffer? 2 megabytes at 400 gig, it's about 40 microseconds, which is a lot slower than the port-to-port latency. And that's per switch. So in the worst case, you might hit full buffering across 7 hops. This is a huge amount of variability. And that's before you get to what I think of as the biggest source of variability, which is the actual congestion and retransmission, which happens in all types of networks, not just Ethernet. So, if you wanted to look at this from an Amdahl's law perspective, where do you actually try to go to remove non-determinism? My opinion, you start with packet retransmissions. You find better congestion control algorithms. You find, better routing protocols. Things that work on demand. You try to reduce buffer contention in the switches, and you try to reduce path lengths. And so the magic question is, how do we get deterministic performance without congestion, without breaking the power wall? And it turns out my company's working on that. Scott in his talk talked about silicon photonics as a technology of the future. Intel's been shipping silicon photonics-based optical switch optics, en masse for the last bunch of years. That's the left side. We've demonstrated co-packaged optics with Facebook, which is the switch chip, instead of having electrical traces to the motherboard, now has optical ones, and you actually go natively directly out. And then the technology that I'm most excited about is optical I/O, where using the same techniques in this middle box, we actually connect directly to the CPUs or the GPUs and have an optical line instead of a bus that comes out. I will skip this in terms of time and go to my favorite and last slide, which is our second to last slide. And if you imagine something that looks like on the right, where we have a job scheduler that communicates with an SDN controller, then programs optical circuits through the network. A circuit is a dedicated piece of hardware. It has no contention. And then the idea is you could actually, with this model, unify the network inside your device with the network outside your device, and have an end-to-end, by which I really mean CPU to CPU, memory to memory, optically switched network. This does assume that communication patterns can be predicted, but I claim that's a much more solvable problem than all the rest of the things that we've talked about here today. So in conclusion, there's been historically differences between the networks inside and outside your servers. Today, there's this apparent trade-off between scale and non-determinism. There's this power density and power wall. We'll call them headwinds, if nothing else, that kind of limit our ability to scale. But my claim is that the next generation of fabric is going to be based off of these optical technologies where you actually use optical for I/O local to the device, and then scale that out across the network. And that gives you predictable performance and unifies these two networks, which honestly, I believe is kind of an artificial boundary. And on that, thank you very much.